All right, so this one is on calculating average atomic mass. You'll see the average atomic mass on the periodic table all the time, like when you have carbon, there's carbon, you have the atomic number 6, and there's always this 12.01 dot 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 there. This is the average atomic mass, and in this video, we're going to be going over the notes on how to do this. So the goals for this video is we have, this is all part of Standard 2, differentiate and explain what causes ions, isotopes, and nuclear reactions. Specifically explain the average atomic mass concept. So the goal for by the end of this video is you should be able to explain what the average atomic mass is and calculate the average atomic mass given necessary info, or basically use average atomic mass in different ways to answer questions. So the concept of the average atomic mass is most elements occur naturally as mixtures of isotopes. We've been working this already in class. You have carbon 12 and you have carbon 13 and you have carbon 14. All of these, remember, are isotopes. And if you don't remember what isotopes are, they are things that all have the same number of protons but different number of neutrons, so they have different masses. So the mass numbers on the periodic table are based off of a weighted average of most of the most abundant isotopes mass numbers. So this is based off you do this in your class all the way, like in our grade book. We're back to it, where you have your grade that is, we talk about being 80% summative and 20% formative. And you've had that your entire, probably at least middle school to high school career, where a teacher says, okay, X percentage of your grade is tests and X percentage of your grade is homework. And it kind of, you might not have understood exactly what they use that for, but you knew that if it was a higher percentage, it means it was a larger part of your grade. So by the end of this, you should actually have a better understanding of what the heck people do with their grades as well. And so the average atomic mass of an element is the weighted average mass of what we call the naturally occurring sample. So this is when we go out and collect a sample of an element, what percentage of that element is each of the different isotopes. So that's what I mean. So we also use the phrase natural abundance. Natural abundance. So how much of each of these isotopes are in nature? So let's start with carbon as an example. So carbon. You see that the average atomic mass of carbon is 12.010. This is decimal, but we've already talked about you can't have half of a proton. It does not exist. So everything is normally whole numbers. All the stuff we've done with isotopic notation has been whole numbers. So why is this a decimal? Okay, well, that comes down to the average atomic mass concept. So here's an example. So the two most common elements of isotopes of carbon are carbon 12 and carbon 13. Okay, so if you went out in nature and you got a sample of carbon, 98.89% of it would be carbon 12, and a tiny little 1.1% of it would be carbon 13, and carbon 14 is even rarer. Okay, so carbon 12 has a mass of 12, carbon 13 has a mass of 13.3. And so the average atomic mass is 12. But your math, you know that 12 plus 13 divided by 2 gives you the average is 12. That should be 12.5. Why is this 12.01? Well, it's because it is weighted. So when we say weighted, it means we're taking into account that there is way more carbon 12 and a tiny little bit of carbon 13. And so that gets factored into this. So here's how it works. So to calculate the average atomic mass, you multiply the mass of each isotope by its natural abundance, which is always a percent, expressed as a decimal, and then you add the products together. So just as a quick review, make sure we're all clear on percent. So if you had 75%, 75% is equal to 0.75. right? Or 98.86% is equal to 0.9886, okay? So that is the natural abundance as a percent, or expressed as a decimal, okay? And then we add the products. So here's an example. Rubidium has two common isotopes, Rb85 and Rb87. Okay. So remember, these are the isotopes. That means Rb85 has an atomic mass of 85, and 87 has a mass of 87. And the unit we use for these is called AMU. You'll see that throughout this. That stands for atomic mass unit. It's basically it's 1 AMU is equal to 1 proton. So it tells you about how much it weighs. And you also remember that that is also the same as 1 neutron. Okay. So if the abundance of Rb85 is 72.2% and the abundance of 87 is 27.8%, what is the average atomic mass of rubidium? Okay, so these are our two pieces of information. Let's see what we can do with them. So we have our isotope, our rubidium-85, and we have this relative abundance. So first thing, we have to turn our percentage into a fraction. So 72.2 turns into 0.722, and we got to do this for the other one. 27.8 turns into 0.278. Okay, so there's the fraction. And then the mass, well, we have 85, so that's the mass in AMUs. So rubidium-85 is 85 AMUs. I know, clever, right? Really hard. And then rubidium-87 is 87 AMUs. Okay, now we just multiply the two together and add it. So 0.722 times 85 is equal to 61.37. And 0.278 times 87 is equal to 24.186. And then we just add the two numbers together. So we have a total mass of 85.86. So that means our equation is the percentage of isotope 1 times the mass of isotope 1 plus the percentage of isotope 2 times the mass of isotope 2, and then dot, dot, dot. In this case, we only have two isotopes. We're done. But if we had more than one isotope, like we'll see in another example in a minute, we would just keep going, and then you add it together. That equals the average atomic mass. So I hope you're seeing it's really just percent times mass plus percent times mass. That's all it is. So let's kick it up a notch. All right, so now this is where the fact that you're in algebra comes into account, right? So here we have a bunch of information. We know, given the average atomic mass, so we have the average atomic mass of chromium is 51.996 AMUs, and the percent relative natural abundance of each isotope, so we have all these percents right here. Calculate the identity of the unknown isotope. So this is one, so this is where algebra comes in, okay? So our unknown mass, our unknown chromium is going to be X. Okay, so we're solving for X. We already know that it's the percentage of isotope 1 times the mass of isotope 1 plus the percentage of 2 times the mass of 2 plus the percentage of 3 times the mass of 3, dot, 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 we keep, and then well, actually in this case we'll just keep going, so plus the percentage of 4 times the mass of 4. And all of that is going to equal our average atomic mass, which in this case, so average atomic mass. So in this case, that's going to be 51.996. So here's the thing, we have all these numbers, we just plug them in. We know that X, chromium, we want to find this chromium, so this is our X. So we're going to take that X, and that X is going to go here, and then the rest of the numbers we have, so we plug it in. So I'm going to the next slide where I have all that set up. So once again, our unknown is X, right? So we put that in here. So this is isotope 1, where we have an unknown mass and we know the percentage, which in this case was 4.345, so we turned into 0.045. And then we have isotope 2, which tells you that it is 52. And then there's our percentage. It was the most common, so it's 83%, which is 0.8379. And then we have isotope 3 plus isotope 3, which is 53 times 0.950. And then finally we had isotope 4, which was a mass of 54 times 0.02365. So this is isotope 4. And all of this equals 51.96. So now we bust out our calculator and we start plugging these things in. So we get, remember our math, I'm going to write it up here on top. We get, so here, start with isotope 1, so it's 0.04345x plus, go on to our next one, and I don't have all these numbers pre-worked out, so I'm going to solve them right now. 52 times 0.8379, so that's isotope 2, so it's plus 43.5708, plus isotope 3, which is 53 times 0.0950 is equal to 5.035. And isotope 4, which is 54 times 0.02365, so plus 1.2771, and all of that is equal to 51.996. So now we simplify, we still have 0.04345x plus, that's going to be 43.5708 plus 0.035 plus 1.2771, all that together. All of these together is equal to 49.8829, and that is equal to 51.996. So now we subtract 49.8829. We subtracted this side, so 49.8829. So 51.996 minus 49.8829 equals a number. So 0.04345x is equal to 2.1131. So we divide this side by 0.04345, divide this by 0.04345, so divided by 0.04345. So x is equal to, is that right? X equals 48.6, so we're going to round that to 49 because it has to be a whole number. So we have a rubidium with a mass of 49. Yes, it's a lot of steps, but is it actually that hard? No, it's not. You shouldn't see it as that hard. You just kind of add them all together. Okay? All right. One more example. All right, so one more example. So chlorine has two naturally occurring isotopes. The mass of chlorine 35 is 35 AMUs, and the mass of chlorine 37 is 37 AMUs. Just a footnote. It's actually not completely true. It actually works out. Sometimes if you're seeing problems, you might see the mass of chlorine 35 listed as 34.696. That's because we act as if a proton is exactly equal to a neutron, but neutrons are actually slightly different in mass, and then there's also some Einsteinian stuff that you are welcome to Google it, but it doesn't help. So it's not exactly 35 due to some weirdness, but we're going to pretend. Okay, so just so you know, this 35, yeah. So the mass of chlorine 35 is 35 AMU, and the mass of chlorine 37 is 37 AMU. Using the average atomic mass from the periodic table, in this case, 35.453, find the abundance of each isotope. Remember that the sum of the two abundances must be equal to 100. So this is algebra. Yay, algebra. So for algebra, you have to be clever here. So basically, we have to remember that if the mass of 35 is equal to X, chlorine 35, then the mass of chlorine 37 is going to be 100 minus X, right? Because both of them together have to be equal to 100. So this is algebra. Yay! I see. When are you going to use it? Right here in chemistry. Yeah! All right, so we're still using our same basic equation, which is the mass times the percentage. But in this case, we don't know what the percentage is, so we're going to be using our x's and our x minus 100. So let me show you how we set that problem up. All right, so we have x is equal to the fraction of the relative abundance of chlorine 35, and we have 100 minus x is a fraction of abundance. But here's the thing, remember, this 100 minus x, this is in percent. So if we're going to do this, we actually have to we have to get this out of percentage. We have to have it as a decimal. So that means it actually is 1 minus x, because to convert 100 to a decimal, 100 to a decimal is 1. So this is actually 1.0 minus x. Okay, that makes sense. I hope that makes sense, because remember, percent to a decimal, you divide by 100. 100 divided by 100 is equal to 1. So we get 35x plus, well, 37 times 1 is 37, minus 37x is equal to, I just like colors, 35.453. All right, so now we have to simplify. So 35x minus 37x is negative 2x. And on this side, if we have a plus 37, then if we have a plus 37, we have to have a minus 37, so we minus 37 over here. So 35.453 minus 37 is equal to negative 1.547. We factor out the negative 1, so we end up with 2x equals 1.547. So x is equal to 0.7735, which is a percentage would be 77.35%. So that means chlorine 35 is equal to, has a relative abundance of 77.35%. So if we need to find chlorine 37, well, it's 100 minus x, or 0.1 minus x. So 100 minus 77.35 is equal to 22.65. So that's the relative abundance of chlorine, which I can't spell apparently, chlorine 37. This is about as hard as it gets, guys. This is algebra, but it is still algebra. You got to think it through and work your way through the math, but it does work out. So this is your calculating average atomic mass. There's a worksheet. It is worksheet 8 that you should be able to do after this. There's a second video attached to that by somebody else walking through some of the problems. So you're welcome to watch that if you don't like my explanation. But I'm hoping this should do ya.